Hello, in this tutorial we'll be discussing source and target types, which will be released in the new version. So then the user will have the possibility to select different sources types and different target types, and what that means for your model and your accuracy and your calculation speed is what we will discuss today. So now, why is this important? Basically, you always, in Rat, the calculations are based on direct BO/var, so that's an integration method. And this way, there doesn't need to be any meshing of the air, and it's sped up with the multi-level fast multipole method. The MLFMM is already explained in the previous tutorial in this series, so I will put this in a video list basically. And so in the first tutorial we will explain the multi-level fast multipole method, and then you get a feeling of how the settings of element size affect the speed of your calculation. But the other thing that affects speed and also accuracy of the calculation is the source type. Now, why do you want like very high accuracy? Because in many cases the user is not recommended actually to change it, and that's why there's this auto setting, and the auto setting will pick a setting for you based on some criteria that we'll discuss later. However, why the auto setting also does not always select the most accurate, but it takes into account the combination of accuracy and speed, because usually when you're designing your magnet, you don't want to spend like endless time waiting for the calculations to be finished. So the auto setting picks the best setting that is the fastest and the most accurate, and that doesn't always mean it gives you the best peak field. Now, peak field is important when you are using superconductors, because basically the peak field determines your margins, your temperature margin, your load line fraction, and so on. So if you're really designing on the edge of your margins, you really want to have a very accurate peak field, and that's one of the reasons why you could play with these settings here. And the other one is when you look at the targets, there's only basically two options. You can do the nodes, the Gauss points, and a combination of the two. And this actually only becomes important when you want to look at the force density. That is what we'll be discussing today. And we'll do that together with this sheet where the different source types and also at the bottom the different target types are explained. So first, what are the sources and the targets? It's quite simple. The source type defines how the coil's current distribution is represented in the model, and the target type defines where the magnetic field is evaluated. So that's why it's important. Now, there are different, in the end, there's 5 different source types. For 3D, they're all available. So you have Gauss points, centerline, analytic, line currents, and Soleno. And if you go to less and less dimensions, because it's possible in Rat to, for instance, model only a surface or a line of your coil, less and less options are available. So for 3D, we have them all. And by default, the line currents is used, and most people are actually modeling in 3D, and so by default you use line currents because this gives you the best combination of accuracy and speed. Now, how does that work? The line currents, basically the calculation in Rat is done by direct BO/var evaluations of the field of a source on a target, right? That's BO/var. So the current of the source is creating a field on a target, and usually this would mean that this is a very slow type of computation because you have to evaluate for each source on each target, which gives you source times amount of targets times of complexity. However, in Rat, as we already discussed in the previous video of this series, the multi-level fast multipole method is used, and that's why it's faster. Now, as I said, there is a different video for the multi-level fast multipole method, and it's probably good to check that out first because it also has to do with calculation speed and accuracy. The main importance there is keep your elements as sort of cubic or spherical as possible, so don't make them very long, don't stretch them out. And sometimes it may be faster to have more elements, because then the multi-level fast multiple level methods can do a better division of the sources and the targets in different multiples. Now here we are actually looking at the type of sources and the type of targets. And so again, the sources define how the current is basically represented. And there's different versions of the Biot-Savart basically used then to do the integration. So now the default in 3D is line currents. And so what happens there is basically the line currents are used to approximate the coil as filamentary line elements, line current elements, and this mimics a distributed current field. This was first demonstrated in the jackpot model, so I'm talking about these filaments here, and the jackpot model was basically also using the multi-level fast multipole method. So the combination of line currents and MLFMM is already quite well known. So these line currents basically connect. So if this is an element, so these boxes here represent elements of your coil. So there would be many more in front and many more in the back. These line currents basically represent current that goes from the phase where current comes in from the previous element to the next phase where it goes out to the next element. So these line currents connect the current from one element to the next. And you see that here as well. If you're modeling surfaces, current would come in here, go out there, and the line current is how your current is represented in this source type. Now, the way these line currents are distributed is by first calculating basically the Gauss-Legendre points. And so that also comes in here a bit. So another way of calculating or representing your current distribution in your element is by using Gauss points. And Gauss points then are sort of points inside your volume, where these are Gauss-Legendre points, right? So you try to represent the element by sort of point currents, and that's also a way of calculating the magnetic field. And each point is basically assigned a portion of the current based on its location and weight. And this calculation of where the point should be is done based on the Gauss-Legendre points. And this is not very accurate, but you can influence the number of points with the setting over here. So if we go to your coil settings, so the source types and the target types is something that's defined in the coil settings. So not in the calculation settings, but in the coil settings, because it's basically a parameter of how your coil is modeled. So you can change the number of Gauss points with the n-Gauss parameter. The more points you have, obviously will make your calculation more accurate. However, it also makes it more slow, because the more Gauss points, the more evaluations. There's also this parameter called softness. It's the softening factor, because this basically helps you have a smooth transition at like boundaries, right? Because softness prevents singularities by modeling each Gauss point as a sphere of distributed current. And so that would mean that a softness of 100%, the current is fully enclosed in the spheres. However, from experience with the multi-level fast multipole method and the Gauss points and also line currents, it's known that the softness should be a bit higher. So this current distribution should be a bit further than the spheres. And so the default setting of 140% is actually what you should leave in most points. Now, I was talking about the line currents before, and the reason I went back to the Gauss points is because the location of where the line currents are drawn is based on where the Gauss points would be if you would use Gauss points, right? So you calculate for the phases where the Gauss points would be based on the Gauss-Legendre criteria for these Gauss points. You assign a weight to them, and that's how you distribute the current over these line current elements. And this is quite accurate and indeed also quite fast. So that would be the default setting for most cases. Now, there is other options that you can choose. There's the center line, and that's basically a special kind of line current, because instead of having multiple line currents in your volume, in your element volume, you only have one. And this actually only works or should only be applied to when you have conductors that have a round cross section, right? So this cross section is rectangular, that's not great. But if I take another simple coil, so this is it has a point cross section, but in fact I'm gonna change the cross section to a circle. So if this would be your coil where you have like a round wire in a loop, then the center line makes sense. And it's great because actually what Rat does, it only draws one line. So instead of having these multiple lines, it only draws one line, and it's assuming, in fact, that your cross section is round. And based on that and Ampere's law, it's calculating the current distribution from the center to the outside of your cylinder, which is linear, and that's a very accurate representation of a round wire or a round cross-section, round conductor. And in fact, it's also very, very fast in this case, because there's only one line, right? Because here you use like multiple lines. Even if you have a round conductor, you can use the line currents, but you would have multiple lines in your cross-section, because these the current distribution is calculated slightly differently. It's not based on like this linear going from the middle to the outside. It's not linear distribution and it stops on the outside of the circle, but because we use line currents, it's a slightly different weight for each of them, and the smoothness is applied a bit further from the edge, right? The smoothness goes to 140%, not to 100%, because here the smoothness factor would by default be 100%, regardless of what you said in the center line. So for a round wire, this is actually almost 100% accurate and very fast. So center line can be applied to round cross sections only, because otherwise the assumptions don't make sense anymore. And it's then the most fast and the most accurate. So we had now these three. Then these are all still assumptions of how the current distribution is inside your element. But you can make a different assumption, especially in the case of rectangular or quadrilateral, so non-round conductors. There is the analytical source type, which represents the current in sheets. So you have current sheets here inside your volume element, and the more sheets you would take, the more accurately it becomes. And if you would take an infinite amount of sheets in each element, you would have 100% accurate calculation, because in Rat there is a analytical representation of the current in a quadrilateral sheet. And so that means there is an exact solution for the current in a rectangular or quadrilateral sheet. And so the only reason why this would be less accurate is because you would have only like one or two sheets over a very large volume element. So what's the downside here? It's slow, because this calculation of the surface current here on this quadrilateral sheet is a very long equation that takes some time to solve, and there's exponents in them, logarithms and that kind of stuff. So it is in general much slower, right? Here there is a much simpler representation. The current of a line you can much easier calculate. And so this one is a very long equation. And in addition, at the moment, there's no GPU acceleration for the analytical. But it is the most accurate, especially if your conductor is not round. So if it has a rectangular cross-section, like in many cases, I would say. So here, the analytical would be the most accurate. But then again, it's also the slowest. So why would you use this? That you would use in case of peak field. Then the last one is a soleno, and you see that there is a solenoid drawn here, and that's because soleno elements are only used on solenoids. The reason for that is that instead of taking these rectangular current sheets, the sheets are represented as like cylindrical current sheets. And so that only is the case for solenoids. And so these coaxial current sheets are used to allow for elliptical integrals of calculating the field. And then in combination with Richardson extrapolation, this gives you a very high accuracy. So that's something I didn't mention here yet. But the analytical and the soleno, in order to avoid having to calculate like infinite number of sheets in each volume element, they do Richardson extrapolation. And that makes sure that you know the field very accurately, even though you only calculate the field of only 10 sheets or something like that in your element. So soleno, there is an exact analytical solution for the current sheets of this form. So for the cylindrical current sheets, you can use analytical elliptical integrals to calculate the field. That gives you an exact solution of this circular current sheet. And then by using, for both the analytical and soleno, the Richardson extrapolation, you gain a bit of speed and you keep your accuracy. So that's the explanation of these sources. Now, how does it go in practice? Now, first of all, I only mentioned this briefly, but I think it makes sense that for 2D models, you can only have like the Gauss points, the line currents, or the analytical. The center line doesn't apply here because, you know, there is no round conductor. There is a 2D flat surface. And soleno doesn't apply because, again, it's just a surface. Although a solenoid could also be a surface, but that's like, in most cases, soleno doesn't apply. And in 1D, you can only have Gauss points and line currents because really you're only looking at a line here. So now let's go to Rat and let's look at the implications, because again, the importance here, why are we talking about this? Because you want to keep your speed while maintaining your accuracy. And in many cases, line currents would therefore be plenty accurate. But for peak field, you want to use analytical because you really, really want to know it very, very accurately. And maybe for round wires, you can use centerline already because it's very accurate and still very fast. So now, how do we demonstrate this? Let's go to Rat. So again, I go back to my loop model, because let's start with this center line here, and compare it to line currents, because line currents would be the default. So how do you set this? You go to your coil settings, and inside the physics here, there is the number of Gauss points and softness, which affects the source type. But in fact, it starts with the source type. And again, the source type, it's a physical parameter because it is used to represent your current distribution in your cross-section, in your coil, in your element. So by default, it's a 3D object. So by default, you would get a line current. So let's force it that way, because then it's clear. I'm not touching the targets, we'll do that later. So let's look at the plane calculation and what it looks like, because actually I want to demonstrate the accuracy here. I leave the default softness. Softness is something we're never going to touch. I can't think of an example when you want to change that. Softness is just based on experience. This is the right setting. You could change that, but I don't think you'll gain anything. Number of Gauss points we can play with later, because that determines how many line currents in the end are in this cross section. Our cross section is a circle. So let's start with line currents and let's look at the plane. I'm gonna remove all these to make it easier. Let's look at the plane. And why is this important? Well, it's important at the boundary conditions. And that's why we need to have a highly accurate calculation. And we only need to look really at the boundary. So I'm gonna make this smaller as well. And move it, in fact it can be in much more small, it can be half, and then we move it in Y to have it around sort of this this cross section. Let's do the calculation. So again, we have the setting for line currents and we're finished here. So let's look at the boundary conditions. There you go. I'm gonna try to exaggerate. Now at the boundary, so inside the conductor, the field is lower than just on the edge, and then towards the outside it becomes lower. And you see here, the field is higher than on the other side, and we can show that. So Z in our case is, so we're now, this is the Z direction, so this is okay. But it's upside down axis like this. So if we turn this upside down, this is how we're looking at the field distribution, right? Because the peak field is highest here, so towards the inside of the coil it's higher than towards the outside. Alrighty. Yeah, because these are higher numbers, so higher radius means lower field. But if we zoom in, this is actually slightly wobbly. Maybe I can exaggerate it even more if I have like a few more points. So on the boundary, the field is actually not, you would expect here smooth round lines, and that's the downside of center lines here. You see it not much better here. I was hoping to have like even more wobbles, but okay. Maybe we can exaggerate it by, no, that would result in a center line of 1. So anyway, so in this case, for the round conductor, when you use line currents, you don't get a nice smooth field here. In fact, there's some noise. So if we then go to the center line, which is this setting, it should be better, because for a round conductor, this is almost 100% accurate, especially on the boundary, and that's really where these settings make the biggest difference. It's finished, so let's look at the difference. I'm going to compare those side by side. So this is line currents, and this one is center line. And you see here, if we zoom in, it's actually much smoother. Now these non-round pieces here is because we have not enough targets probably. So this wobble and this noise here especially has been resolved. So this would be the reason to use the center line. It's much more accurate in the loop situation. All right, so then since we have a solenoid, this one is not a solenoid with a rectangular cross section but a round one, but let's say we have a solenoid with a rectangular cross section, right? This would be the ideal case for Soleno, because Soleno assumes really a rectangular cross section, but by default for 3D, except for solenoids, I'll go into that later, but this would be sort of your default setting, so the line currents. Let's make it a bit longer. Oh, no, I actually meant longer. Yeah, so the solenoid becomes a bit longer. We also have to grow our XY plane a bit so that it's sticking out. So this would be a reason to use Soleno type elements, but by default, let's say we're using line currents. Maybe I should have put less numbers here again, because I'm not sure if we need all the target points. I'm going to cancel this. This is actually interesting because not only should this type be slower than Soleno, but it should also be less accurate. Well, it's finished, so we have less target points. There you go. But you see, we're using line currents, and you see again there is a bit of an inaccuracy here because there is a bit of noise here at the boundary conditions. Here at the far away point, it's not so important, the effects of the element types, because far away from your current, it doesn't have such a big effect. It's really the boundary where it has an effect. So now, since we have a solenoid, let's go for Soleno. And Soleno is an analytic solution for a circular. Wow, that was like extremely fast. I didn't expect that myself either. It's an analytic solution, and you see here. Wait, let me put it below, and you see that for this solenoid, this is still slightly wobbly, and here I can zoom in, but it's completely smooth. So that's Soleno. It's really an analytical solution of these current sheets. So if you would use line currents for solenoids, you get less accurate results. So that's why you would apply Soleno elements. What else have we got? Right, actually, I didn't point this out to you yet, but this was for the line currents, and this was for, oh, excuse me, not the result. This last one was for, it doesn't show the time. Oh, that's a bummer. Oh, that's interesting, actually. I didn't know that. So Soleno doesn't actually show the time. So let's exaggerate by taking the circle and making the elements half as small. So that gives, oh, excuse me, half as small. So that gives us more elements. Typing is difficult today. So this gives us more elements, and now we do still have Soleno. So maybe we can have sort of a feeling of how long it takes. I started now, and it's immediately done. I think it's less than a second, but I can't tell from the logger, sadly. Let's go back to line currents. So this would be less accurate, but also slower, even though the other one is an analytical solution. So I can talk here for a while. It takes a few seconds. Show log, it's still not done. See, so this line currents, even though in most cases it would be fastest, in the Soleno case, it's even slower, even though we have more elements. So we have made it easier for the multipole method to do its thing because we increase the number of elements, but it's slower. And it's still not accurate, so that's quite nice to see. So Soleno is for solenoids, it's the go-to option. It's accurate, it's the most accurate because it's an analytical solution, and it's the fastest. All right. Any other type of coil, like a racetrack. So a simple coil would be a racetrack. Here you can't use Soleno because it's not a solenoid, so there's no analytical solution for a shape that has a racetrack, at least not in red, and therefore by default line currents again would be taken, and so I go look at the plane. So I remove this again and I make the plane a bit more with a bit more points, and we're again more interested in the boundary location, but I can make this half and move this because we don't need to know anywhere else. Excuse me. No. Could have looked at the so okay, we're interested in this area and in the boundary, and I calculate 1,000 points. So by default the racetrack in auto mode has line currents. I just click that here because it's easier to visualize. It is fast, right? So it's immediately done. So that's nice. But at the boundary, it's a bit wobbly. And so in most cases, that's okay. If you're not actually interested in the boundary, it's fine. If you're looking at the field of the whole plane and you want to know accurately what's inside of the coil, so the center field, right? That's no problem. But at the boundary, this is a bit inaccurate. And so in that case, we don't have the option to go to Seleno, but we do have the option to go to analytical. So here I go to analytical, and I don't change any other settings. Now I calculate. The change here actually makes it also faster. Show log. No, absolutely not. So it's definitely slower, is what you would expect. But is it better? I expected it's better, and it is indeed better. There's not so much noise on the boundaries, and that is where analytical really is used for. And so it's nice for the boundaries. Not only that, if I add a mesh calculation, is where I would get my peak field from. Now I'm using the analytical result, so I'm gonna move the plane out of sight. This is the mesh calculation, because I'm doing this because I want to know my peak field. So I'm analyzing the peak value. Here it's 8.2. So this is the analytical solution. If I actually change this back to line currents, which is what my default would be, this took us 1.7 seconds. Now the mesh calculations, oh yeah, okay, it's probably faster. This took us like less than a second. Show log. Yeah, really almost instantaneous in my in my life, basically. Peak value. The peak value should have changed. Yeah, in fact, it's a huge difference. It's almost 1 Tesla difference. So the peak value for the peak field here is really not that accurate in the line current situation. Now let's look at the center field actually, because let's add a plane calculation. Because what if we're just interested in the field in the center? So that's not at the boundary, it's far away from the boundary. 200 times, well, let's make it nice and accurate by at least having enough target points. But we can be, we only want to know the field there, right? So, okay, as I said, I'm using line currents. Heat map. So here the field is 1.3 Tesla in the center. And now I change this to analytic for this plane calculation. No, well, for everything, but I'm doing the plane calculation again. It's much slower, but I'm expecting not a great difference here anymore, because in fact, I'm away from, oh, excuse me. Oh, I'm doing the wrong plane. This is the plane that I want to calculate. So it is slower, but I'm expecting the same kind of field. And in fact, it's 1.3 Tesla. So that's the importance for the analytical, right? So the analytical takes more time, but on the boundary, which is where the peak field is, because that is really, your peak field's always on the conductor, not away from the conductor. On the boundary, the analytical is very accurate, but much slower. Far away, so in the center, if you're looking at really like what I'm looking at here, if we're looking at the field in the middle, so not on your conductor, the line currents actually give quite an accurate result. It's not different from the analytical, but the analytical is slower. It's like, in this case, I think it's 5 times slower or something like that. So this, oh, excuse me, I should look at the log. I have all these windows open. So the log here says 0.8, and here, oh, it's not that different. Okay, it's not that different, but if you imagine this is a simple coil, imagine you have a very complicated coil and you want to know the field far away from your coil, it's really not important to use analytical. In fact, it makes it quite slow. You can always do the analytical, but it doesn't gain you anything. It doesn't gain you in accuracy. Far away from the coil, you don't gain anything. And in fact, you lose on the speed. So analytical, if you're worried about your peak field and what the calculation of the peak field is, use analytical. If you're far away from the coil and you're just looking at the field shape, so also for calculating the harmonics, right? So for many harmonics are usually used for like accelerator magnets. So let's say a simple CCT, you want to produce like an accelerator magnet and you want to know your harmonics. You don't need to use analytic, even though you might think like, oh, but it's the best representation of the current distribution in the coil. Well, that's true, but it doesn't have a large effect far away on the coil. And since your harmonics are calculated not on the surface of the coil, just use line currents, which is the default. So in summary, line currents are always used because in many cases you're not directly interested in the what happens at the boundary. You're more looking at the big picture because you're producing a magnetic field somewhere else. However, if you're worried about peak field and you don't have a solenoid, go for analytical. If you have a solenoid, always go for Soleno, because not only is it the most accurate, it's almost 100% accurate, but it's also the fastest for solenoids. So even though compared to line currents are usually faster, not for solenoids. If you have a model where you have a round wire, you're modeling a round wire, then use center line because that's very fast and very accurate. Gauss points, they are there. I haven't demonstrated them very much. In fact, I can go back to this racetrack model. I can set it to Gauss points, but expect the result to be even worse. So let's go to the mesh calculation. This was our analytic. This was our line currents. This is our, whoopsie floops, this is our Gauss points. And it's also different. So it's close to line currents. Maybe that's because the number of Gauss points, I haven't really played with that. But Gauss points also doesn't give you a very accurate results, and in many cases even less accurate, and it's also a bit slower. Gauss points, why they are there is because the line currents is sort of the default implementation, but there is you can check the result by increasing the number of Gauss points. You can check your results of the line current. So this was basically used by the developers to confirm that the line currents implementation was okay, because by increasing the number of Gauss points, you go to a regime where you have these line currents. So the other part that we want to discuss today is the definition of the target points. And there's not a lot to say here. There's only two ways really in way they are different. And that is one, the default definition is on the nodes of the elements. So these are hexahedral elements, and on the nodes of them, the normal target points would be situated. But you can change that to move the target points to where the Gauss points would be. So the Gauss points here is also where the Gauss points for the Gauss point source are situated. And also these Gauss points are used to determine where the current elements for the line currents needs to go, and you can move your target points from the outside of the volume elements to the inside on the Gauss points. And this really only affects the mesh calculation, because anywhere else, right, if you look at the calculation, if you look at the plane calculation, the target points are not on the coil but on the plane. So only when you do a mesh calculation, this setting is actually taken into account. You can also do the combination of both, but really, in general, setting it on the nodes is good enough. And you can make it slightly better when moving to the Gauss points, and this really only has an effect on the force density calculation. It's because when you calculate the force, you do that on the volume of the element, so sort of inside it, because you're integrating. So when you then keep the default nodes targets points, the force first is calculated inside the volume on the Gauss points, and then Rat extrapolates it to the nodes. So there's an inaccuracy there because of this extrapolation. So if you want to have an accurate force density, you change your setting for the target points to Gauss points, and I can show the difference here. So normally if you have the default racetrack, you would have the auto source type with nodes, and if I then calculate the forces, I go to settings, physical property, force density, and if I go to analyze and click on integrated forces, I see that if I have integrated in all directions, it's not 0 for Fy. And that's not what you would expect, right? Because this solenoid, the racetrack should have equal force in minus x and in minus y. It's even more clear because this is kilonewton. So if I change the units in the settings for force to newton, it's about 4 newton. So that's unexpected in principle. So if I change to Gauss points for the target type and I do the same calculation, mesh calculation, and go to settings, force density, analyze, integrate, now it's 0 everywhere, 0 newton after integrating the forces. So if I even go to a finer, so now the forces are in millinewton, it's still 0. So this is because there's no more extrapolation from where the force is initially calculated to the outside. So really for the most accurate force density on your mesh, you would go not to auto, because then red selects line currents. You would go to analytical, keep the Gauss points here. You can even increase this and then do the mesh calculation, because then your force density map that you get as a result, this will take a while because we set it to analytical and we increase the number of Gauss points, but this will really increase the accuracy. As I said, so for all the other things, it doesn't really make sense to use this high accuracy, because for the targets, usually it's either on the plane or on the volume, on the line. So anywhere where you don't do the mesh calculation, this target's type doesn't have an effect. And so the number of targets here is just basically what you said in the discretization. So this is how you can increase the number of targets for plane calculation. So now this would be a very accurate force density calculation. And it's interesting, if you look, for instance, at the field component of Z, you see that here it's negative, there it's positive, right? So it really balances itself out, the forces. And if we integrate the forces, it's 0 in all directions. So the integration, summing up the forces, gives you 0 for this setting. Now, if you want to export the force density so that you can import it in a different program, you don't actually use Gauss points. And this is a bit, you would say, like, why? It's less accurate. However, other programs tend to actually use the force on the nodes of the mesh because they have a different mesh. So no matter what you do, Rat will export the force on the nodes. So even if you have set this to Gauss points, Rat will actually export the force on the nodes to make sure that it's compatible with whoever is receiving your force density table, because they are expecting the forces on the nodes. So when you do export force density, you will automatically save the forces on the nodes. So really, you say, if this is only really for the forces, then in general, if you do not do a mesh calculation, just use auto and nodes, unless you want to know the peak field. Then you want to change your source type to analytical, but you can keep your target type to nodes because you're not interested in the forces. And so for the peak field, this is different. You actually want to know it on the edge, and so you can keep the nodes. When do you touch the target type? You touch the target type when you want to know the force density. The force density is only calculated on the mesh. So if you want to have a very accurate force density, you change to analytical, you change to Gauss points, because that is where the force is calculated. That is for the force density. If you want to use a solenoid, you use Soleno, or you let Rat decide, because Rat actually recognizes solenoids. Now, one last maybe interesting thing is, if we go to like an example, this magnet, if you have like a combination of magnets, you can, for each coil individually, change the setting, right? So if you want to know if you're sure the peak field is on the solenoid, which it is in this case, for the solenoid, you can set analytical, and for the other ones, you can set line currents, which is actually what happens if you leave it on auto. So for the two outside coils where you're sure that there is not the peak field, you leave them to line currents, you set this one to analytical, and then your calculation is not being slowed down by the fact that you use analytical calculation for all coils. So you can play with the settings, right? So you don't have to, that's why it's a coil setting, it's not a calculation setting. For where you need your accuracy, you can increase the element, or decrease the element size, because that makes it also more accurate. You can set it to analytical, but for these, since you are not interested in the peak field there, well, eventually you are, but the peak field is really on the solenoid, you can make your calculation faster by playing with different settings for different coils. And only when you go and look at the forces, you can go to Gauss points. That's really it. One last thing. So in analytical, there is no GPU acceleration. So in order to make analytical faster but still accurate, you can increase the element size, because it's analytical, so it's still quite accurate for larger elements. However, the math is still much slower and there's no GPU acceleration. Then maybe also important, so we have here the analytical, but this assumes that we have like a non-graded coil. So what is a graded coil? So if we grading, there you go, a graded solenoid, that means that the cross section is not equally thick everywhere. So the cross section here is much thicker than the cross section in the middle. That means you can save on your superconductor. That's why grading would be used. But grading actually is not yet taken into account for the analytical. So when you have a graded coil, you should use line currents, because then the current distribution is sort of averaged for each volume element. So that means that the current distribution is actually different, is actually properly taken into account for a graded coil, because here the current density here is higher because there is a thinner cross section. Here the current density is lower, and that different current distribution is taken into account for line currents, but not for the analytical, not for Soleno, not for the center line. Actually, this for the center line as well, so that's fine. So for graded coils, analytical cannot be used yet, and analytical doesn't have GPU acceleration yet. That's the remarks that I also wanted to share with you today. So that's it for this tutorial. Thank you, and please combine this tutorial with the other one on the multi-level fast multiple method. Bye bye!